nanoHUB.org.
Online simulation and more for nanotechnology.
All right, so as I already mentioned that each material platform tried so far for quantum photonics has certain advantages and disadvantages. And it looks like, this is my opinion, that there is no single material platform which would satisfy all the criteria, actually tough criteria to realize quantum photonics. So it's probably going to be hybrid, not only in terms of materials use, but also in terms of the, let's say, the concept, the notions behind that. So by the latter, I mean that probably many ideas from other fields, such as metamaterials and plasmonics, would play an essential role, because they, as I illustrate today, in some cases, could really make a difference in terms of making stronger quantum effects, which is very critical for practical applications. So, and in that regard, what are the advantages of plasmonics in general, which also could be of interest for quantum photonics, as we will see below? We discussed most of them, but let me just re-emphasize, because that's important. With plasmonics, you could really go low in terms of energy consumption. And the goal now, and several groups work on this, actually have femtojoule per bit. For 1 bit information to use as little as possible energy. And I should say this energy consumption, this is the biggest problem for nowadays computers, because they really require lots of energy. So with plasmonics, because this footprint becomes very small, and photonics in general usually implies much less energy. So it's a very realistic, and several groups work in these directions, basically use as little as only 1 femtojoule per bit of information. With plasmonics, it's, you could enable very efficient coupling to other devices. Basically on chip you could have a number of devices and they would interact with each other, couple, which is very critical in terms of integration. Like you could put a source of photons like nanoscale laser. You could have these interconnects, basically plasmonic waveguide, switches, and all other elements, and all on the single chip. It's important that metal or metal-like material used for plasmonics could serve dual purpose. Because realistically, it's very important to be compatible with existing electronics, because it's a very advanced technology, and it would be just not that wise not to take advantage of the existing electronics. So, and these metallic-like structures could serve dual purpose to propagate surface plasmons, plasmon polaritons, as well as electrical current, and that's important. So it could be used for conventional electronics and nanophotonics based on plasmonics. Because of the enhanced local fields, actually there is enormous sensitivity of surface to anything you place on. Remember, there's like condition for surface plasmon polariton. We look at the surface plasmon resonance, and you could sense even a single layer of atoms because it changed the condition for propagation of surface plasmon polaritons, which means that you also could have on-chip lab, on-chip sensor, critical for a number of applications. Of course, if everything on a single chip, so you could reduce fabrication complexity, basically just planar technology with one ultra-thin layer. And Plasmonics also offers a number of polarization properties, because you really could control nicely the polarization. So that's actually not the complete list, but just some of the advantages of Plasmonics. In the end of the day, as I pointed out many times, Plasmonics is critical because it's touched the means to bring light down to nanoscale and manipulate it there. And I already mentioned that there is lots of efforts in terms of developing new materials which would be compatible with existing electronics, CMOS-compatible for Plasmonics. And here I'm showing classes of materials which currently under investigations, including nitrides, oxides, but not only actually, silicides, germanides. There are many, many materials, and I again briefly mentioned today nitrides and oxides as probably one of the most promising materials to be used for plasmonics and metamaterials, which in turn could be very useful for quantum photonics, and that's the perception, because these things, of course, are interrelated. Material platforms to be used for particular technology, in this case, quantum photonics, and also the ideas which you want to bring to realize quantum photonics. Like in this case, we'd like to use ideas of plasmonics and metamaterials. So what are the material requirements? At least for nanophotonic circuitry, you would like to have to keep losses low. There are some applications which actually take advantage of losses, but for nanophotonic circuitry, we would like to keep losses low. And we know that dielectrics, that's actually a trade-off. Is dielectrics losses are very low, but you are limited by diffraction limit, basically lambda over 2n. With plasmonics, you typically use metal or metal-like materials, and the size of the structure could be much less, few nanometers only, but typically losses are higher. So, and what is really important, that your plasmonic materials should be tunable, similar like we have it in electronics, where you could change the properties, tune your materials, and that's why makes electronics so powerful. We would like to have similar properties for plasmonic materials, and the truth is that if you look at the materials, plasmonic materials largely used so far, it's silver and gold and some other noble materials. Real part of the electric permittivity, as I mentioned, in a telecom is actually huge, like -100, which is sometimes not good, particularly for realizing so-called epsilon near zero material, where you would like to take advantages of materials where epsilon close to zero. I already mentioned that you could have this fantastic opportunity to switch materials when epsilon close to zero. And if you would like to accomplish this epsilon close to zero, or let's say whatever you want, let's say -1 or +1, you quite often mix metal with some other material. But if metal, let's say, has -100, and you would like to mix with some material which has positive epsilon, it means that if you would like effective permittivity bring to zero, that the thickness of metallic component should be like, let's say, 50 times smaller. Let's say if my dielectric has a permittivity +2 and metal has -100, and you mix them and you would like to get effective permittivity somewhat around zero, it's clearly that the thickness or the of metallic components should be much, much less. But if you already work with like 5 nanometers, you cannot go 50 times smaller than 5 nanometers. So the point here that having too large epsilon in magnitude sometimes a problem for some applications at least. But overall, we would like certainly have all these materials switchable. So you would like to change the charge carrier density, control their properties. And as I pointed out, you would like these materials to be CMOS-compatible. Let me be a bit more specific about this, how to control real and imaginary part of this the electric permittivity. So let me just remind you that plasma frequency is proportional square root of charge carrier density. And both real part and imaginary part of the electric permittivity for Drude metal is proportional to plasma frequency squared, right? Remember, epsilon prime and epsilon double prime proportional to plasma frequency squared means it's proportional to charge carrier density. And with gold, silver, you have actually like 10 to the 22 in cubic centimeters. And that's why you have real part as large as -100 telecom wavelengths, but also very large imaginary part, because it's also proportional plasma frequency squared. So in that regard, it might be smarter to use some kind of intermediate charge carrier density, somewhat less than 10 to the 22, maybe 10 to the 21, so that epsilon still would be negative, the real part, but not -100, but let's say -1. And the imaginary part would be also less, because all them are proportional to plasma frequency squared, meaning proportion to n. So that's a simple way, basically make metals less metallic. and take advantage of this. For some application, it is important. And there are heuristically two ways to go. You could either start with semiconductors, which have positive dielectric permittivity, and dope them with charge carriers. So by increasing charge carrier densities, you could bring epsilon prime into negative domain. So, but then the charge carrier density wouldn't be that high as in the case of silver or gold. So you heavily dope semiconductors. Not any semiconductor can be heavily doped. They should have so-called high solubility, like zinc oxide I mentioned, so which you can dope actually up to really like 5, 10 times 21, so which is really what you need. Or the other way to go, you start with metals, but you kind of dilute them. You introduce some dielectric components. And a classical example would be like titanium nitride or other nitrides. So you have metal and non-metallic component and the so-called transition metal. And in this case, you somehow dilute metallic properties, decrease the charge carrier density. Either way should turn out to be very productive, and turns out for telecom wavelength, this way is probably the most promising, like transparent conducting oxides, a good example of them. And for the visible this way, such as transition metal nitrides. And then brings us to this table where now we focus on two classes of material. Nitrides, as I said, that's basically you kind of dilute metals in a sense, make a decrease in the charge carrier density, and oxides, such as transparent oxides. In this case, you basically dope semiconductors with charge carrier densities and bring it to the metallic state, so that the electric permittivity is negative. By the way, all this analysis of materials was done in my group, in our groups, and that was done by Nate Kinsey, who is now a professor at the university. So let's look at nitrides. I already mentioned a bit this material. It really looks like a wonder material because it's very much like gold. And the truth is, we started to think of these materials when we looked at these church domes, which looks very much like gold. But we ask ourselves that would be very expensive because we were on a trip and saw so many churches recently built. And then we found out that people use nowadays titanium nitride. So it's much cheaper and it's actually robust, durable, and it's a wonderful material. But then we realized if something looks like gold, it should have optical properties of gold, right? It makes perfect sense. We started to study it, and sure enough, we obtained that this material actually, in many regards, better than gold. It's CMOS-compatible. It's already used, but for different purposes, like a spacer material, for example. It's a kind of ironical. Copper, which is used, of course, in electronics, diffuses, and to prevent this diffusion, they use spacer made of titanium nitride. And titanium nitride is actually this wonderful plasmonic material, but it's used only like a spacer to prevent the drawback of all noble materials like copper, gold, silver. They are too soft. So, but it's already in CMOS line. That's important. It could be grown epitaxially. Here is an example. This is a waveguide which we grew in our lab, and you could see this single crystal quality, 10.5 nanometer thickness, really beautiful layer of titanium nitride. And you could change its properties by changing the condition of deposition. For example, in this case, we use this magnetron sputtering, and depending on the temperature at which you do this deposition, it could be more metallic or less metallic. So you have this opportunity actually to change the charge carrier density and make it less metallic if you want, or more metallic. Basically, it's in your hands. It's chemically stable, it's biocompatible. This material used, for example, in implants, in dentistry, which is very important it could be used for this biomedical condition. It's refractory, it can sustain very high temperatures. This is very critical because with Plasmonics, we focus light down to nanoscale, meaning that we have very high energy densities. It unavoidably results in increase in temperature. And when it's nanostructures like gold to silver, even like 400 Celsius is enough that your structure would be basically destroyed. There is diffusion, there is creep phenomenon, and the shape changes, and which basically means that you cannot use it in a durable fashion. So that's really important that material can sustain elevated temperature, and titanium nitride is very stable at high temperatures. So it's all lots of advantages, which clearly indicates titanium nitride is a great plasmonic material for a number of applications. In terms of transparent conducting oxides, as I said, you could dope them up to very high numbers, for example, with aluminum or gallium. And we in our lab use zinc oxide. It has a very large band gap, meaning that there is no interband transition. It's transparent, which is important. That's actually what gives the name transparent conducting oxides. They are transparent, but also conducting. And depending on how strongly you dope it, you could bring this dielectric permittivity into the negative domain at telecom wavelengths. But it's not like -100, it's like -1 or 2. And you could control it depending on the depth. And this is crossover, where the electric permittivity crosses 0. And the position where it crosses 0 could be controlled. So we have now negative permittivity, which is not huge. Important for some application. As I said, for a number of applications, like for switching, you would like to see it close to the point where epsilon actually is nearly 0. But if you look at the imaginary part, look, this is gold at telecom, this is silver, and this is transparent conducting oxides. It's dramatically less. So that's all important advantages, and shows that transparent conducting oxides, at least for telecom, could be material of choice. And again, it's CMOS compatible. You could switch, control it optically, electrically switch. So that's really what you need for your material to be functional. And there are well-developed technique for these transparent conducting oxides for other purposes, for electronics. So again, this is kind of material which was not used until recently for plasmonics, but was used for other purposes, and now people pursue it for plasmonic application. So it's a dynamic material. You could have high doping because of high solubility, as I pointed out. There are material fabrication processes already used, like sputtering, PLD, ALD, CVD, all this. It's existing technology. As I pointed out, this material already used, like in displays, for example. It's non-stoichiometric material, meaning that you could really change its property dramatically. For example, plasma frequency here could be tuned in a huge spectral range by changing charge carrier density between 600 to 1600 nanometers. This is like a dream came true. That's exactly what you need for plasmonic materials. So that's all. That I already mentioned that they could have negative, but not that large in magnitude, dielectric permittivity. So that's our other former student, Guru Naik, who is now a professor at Rice University. He actually wrote this very seminal paper on showing the importance of this material, which is now the most cited paper in the journal. So it's just like showed you basically it's like a roadmap for new materials to use. Well, but that's all about materials for plasmonics in general, but how it could be used for quantum photonics. There will be several examples I will be discussing with you, and I will start with one which has to do with single photon source. Of course, we're not talking about quantum photonics. We need to have like single photon sources. Similar like for photonics, lasers of extreme importance. For quantum photonics, when you deal with quantum properties, the ability to generate single photons efficiently is absolutely of critical importance. And it turns out that metamaterials, plasmonics actually could play a role in terms of making these efficient single photon sources. Well, for example, for quantum telecommunication, for quantum communications, people now could send this information for roughly like 200 kilometers, which is not enough. And it's probably to send it for longer distance when you need this quantum key distribution. You probably would be use quantum teleportation and things like quantum memory. And for doing all that, you probably would need single photons. So you would have to rely on single photons, which is emphasizes the importance of single photons. In general, for quantum information, by dealing with single photons, with pair of entangled photons, which you always could make out of a source of single photons, So that's all very critical. It just emphasizes that for quantum photonics, we need these efficient sources of single photons. What are the requirements for these single photon sources? What these single photon sources should be like ideally? So they should be on demand. Not just you should generate single photons probabilistically at some point, but exactly when you need it. That's important. It's called single photon on demand. So you should do it with very efficiency, with high efficiency. Like if I need it at this particular instant with efficiency 100%, I should generate single photon. To prove that we are dealing with single photon, people usually measure this correlation function, so-called G2. If it goes to 0, then it's ideally you generate single photon. If it's 1/2, normally it means that yes, you're kind of in the regime of single photon, but it shouldn't go to 1 or above. So it should be ideally close to 0. Very important thing, not only you should be able to generate many single photons, but also they should be indistinguishable, meaning having exactly the same characteristics, frequency, momentum, phase. And that turns out to be a particularly difficult challenge. To generate, let's say, at room temperature, indistinguishable photons, that's something which has not been accomplished so far, which is very critical. And you would like to have very high repetition rate, like a gun. Many, basically like, let's say, billions or 10 to the 12 photons per second. That's what you ideally would like to have, indistinguishable. And don't forget that eventually you would like to get it into telecom. Either these single photons already should be telecom, which even harder to make, or at least you should be able to convert them, let's say, from visible to telecom. Because eventually you would send it through a fiber, and that has to be around this telecom wavelengths. Well, of course, it should operate on chip, and ideally, as I pointed out, we would like to have it all at room temperature. So if you're dreaming, why you should limit your dreams? But that's the criteria for the ideal single photon source. That's what Paul is now working on, along with our postdoc Semyon. And if he would be successful, maybe he would create a single photon source which would satisfy all these criteria, right, Paul? Next week. So what are the existing approaches to generate single photons? Well, one of them is nonlinear scattering, so-called down conversion. Basically, you have a larger, in terms of energy photon, you generate 2 photons at smaller frequencies. But this is probabilistic. It's not deterministic process. There is always some probability to generate a single photon. And if you would like to increase the efficiency of this single photon, you normally increase the efficiency of the pump. But that increases G2, meaning that you not necessarily generate single photon. You could start generating multiple photons. And that means that G2 is not 0 anymore. So when you try to make the process more efficient, you increase G2, meaning that you start generating not single photons, but pairs and so on. So that's a low use, quite oftenly process, but it has certain drawbacks. Well, with quantum dots, it's of course a great thing, but quantum dots normally tend to operate at low temperatures, because otherwise the bandwidths are very broad, and let's say at room temperature, telecom wavelengths, quantum dots, normally, well, it's not shown that they can generate single photons at telecom at room temperature. So as I said, you normally work at much lower temperature. And of course, you always have this problem of huge dispersion in sizes. Trapped ions and trapped atoms, in principle, it's a great source of single photons. But this is kind of bulky. I mean, it's not really chip compatible. And with ions, is typically what you generate is in UV spectrum. And atoms is very hard to control, to have these trapped atoms. So fundamentally, in terms of demonstration of some scientific things, it is good. In terms of real chip-like device operating at room temperature, it's somewhat hard to envision. And of course, single molecules or color centers, yet another approach to generate single photons. The problem here that, like in the case of like these color centers, they typically couple to phononic bands. And because of this coupling, the line is relatively broad. When the line is broad, it's hard to make generate indistinguishable photons. So still, I mean, there is a good chance, and probably that's the best way to go. For example, you could use particular vacancies which have much more narrow spectral lines because coupling to photons is not that strong, and I will talk about this later. That's exactly what Paul is going to work on, actually. So, but let me first mention what kind of things could be done with metamaterials and plasmonics in terms of increasing the efficiency of generating single photons. So as I pointed out, for nitrogen vacancy, the bandwidth is relatively broad because it couples to because of this phonon broadening. So it covers, you see, roughly between 600 to 800 nanometers, so it's rather broad. But the advantage of nitrogen vacancies, remember, that spin degree of freedom is long-living, which is very good because it could be used as a memory, control optically. And to increase the efficiency of generating of single photons, people use all type of resonators, antennas, and things like this, like gap antenna, like in this case, two plasmonic pieces, like gold, and here you have this very high local fields, high photonic density of states. You could have this increased efficiency in generating of single photon. You could have nanowire, it's like basically waveguide, or you could have some groove, which is also waveguide. So all these approaches to increase the efficiency of generating single photon. And there is one which is kind of an unorthodox. It's different in terms of idea. And the idea comes to work done by Zubin Jacob and Evgeny Narimanov, two of my colleagues. They are both professors now here. And they actually suggested to use so-called hyperbolic metamaterials to increase photonic density of states. And that's a fundamentally different approach, and I would say quite smart one. To make a material hyperbolic, I'll explain it in a moment what exactly it means. You have to make these layers of material. One is with negative epsilon, and the other is with positive epsilon. And what we managed to do in our group, it's actually, honestly, I should say, quite spectacularly in terms of material science. We made this like 20 layers of extremely thin layers of plasmonic material with negative epsilon, titanium nitride, 4 nanometer thickness, single crystal quality. And in between these layers of dielectric, aluminum scandium nitride, when purposely added scandium to match the lattice. It's like one super lattice, one single crystal, made of plasmonic, dielectric, plasmonic, dielectric, plasmonic, dielectric, 20 layers and each 4 nanometer in thickness. It's a quite spectacular result in terms of material science and fabrication. And this material effectively has dielectric permittivity negative in XY direction and positive in Z direction. Because the thickness is so small, 4 nanometers, you have to average over a relatively large size. And when you do that, it turns out that effectively it's negative in XY direction, works like a conductor in XY direction, and works like a dielectric in Z direction. And in this case, it turns out that if you look at either frequency surface, it's given by this hyperbola. Did I? Oh, Jesus. Yeah, somehow I thought I have these slides, but okay. Anyway. If you look at the isofrequency surface in this case, what is isofrequency surface? It's basically, you look at like kx squared plus ky squared is equal omega squared over c squared. And when you do kx squared, so it would have epsilon x in denominator and epsilon y in denominator, epsilon z in the denominator. And for conventional cases, isofrequency surfaces, it's actually like, let's say, for homogeneous and isotropic material, it would be it's a sphere. Kx squared plus ky squared plus kz squared is given by n squared omega squared over c squared. It's a sphere. If it's anisotropic, it would be spheroid. But if one of the epsilon is negative, it actually becomes hyperbolic. So instead of closed surface in this K-space, which represents a constant frequency, you have open surface, hyperbolic surface. But photonic density of states, actually, you need to calculate volumes between two isofrequency surfaces, frequency omega and omega plus delta omega. Since it's open as opposed to sphere or spheroid, actually it's infinite because it goes to very, very high Ks. So and because of that, you have extremely large photonic density of states. But the important thing is you have here also in all type of resonators high photonic density of states, but that's because of the resonance, only at particular frequency. And when you have a resonance, yes, you have very high photonic density of states at resonant frequency, but also such a system is slow, because the higher the quality factor, the longer response time. You involve resonance. Here there is no any resonance. In this case, you have large photonic density of states because of the topology, because of the fact that your either frequency surface is open rather than being closed. So as long as my material is hyperbolic, meaning acting as a conductor in XY plane and as a dielectric in Z plane, meaning so that either frequency is described by this hyperbolic surface, you have this very high density of states. And there is no any resonance, meaning that it could be fast, and also no resonance, meaning there don't have to be losses, because every time you have a resonance, you have losses, resonant losses. So it's really different approach to increase photonic density of states, which in principle makes possible this efficient generation of single photons. So that's the idea, as I pointed out, formulated first by Evgeny Narimanov and Jacob Zubin, and that's what we use when we made this hyperbolic metamaterial. And here is the experiment done by Misha Shalaginov, who is now at MIT. They basically placed this nanodiamond with nitrogen vacancies on top of this hyperbolic metamaterial, which has high photonic density of states, and obtain this increase in efficiency in generation of single photons, which is of course reflected in the fact that the lifetime shortens, because you generate photons fast. Every time when you emit photon, of course, there is relaxation. So the time becomes shorter and shorter when you place your nanodiamond on this hyperbolic metamaterial, and prove that indeed we have single photons. We measured this correlation function, and it goes really way below 0.5, meaning that we do generate single photons. So, and the problem though with these hyperbolic metamaterials, lots of energy stays within the hyperbolic metamaterials. It's not outcoupled, but rather it's associated with propagating waves which have wave vector larger than omega over c, and they stay within the hyperbolic metamaterial. To outcouple of this hyperbolic metamaterial, that's, by the way, shows how many counts, like 500,000 counts we obtain in these materials, which is pretty decent, respectable. Recently, Semyon did more experiments, and he now has 5 million single photons per second. So this result already further improved, actually. We're just planning to submit this paper. And the other member of group actually is undergraduate student, Oksana Makarova. I mean, she came up with design that when you actually make this this ring hole actually within this hyperbolic metamaterial, then the efficiency of outcoupling increases dramatically. So she just published this paper in Optics Letters. Actually, she just started to work in our group, and she's junior in physics here in Purdue. So, and what we obtained that in this case, actually, you have 50 times, 50, increase in the number of single photons collected by a detector. It's a pretty spectacular work for undergraduate student, I should admit. So, but this is an example when metamaterial ideas, in this case hyperbolic metamaterials, which provides larger photonic density of states, can be used to increase the efficiency of generation of single photon. So, and I think that's really the way to go, to look at how plasmonics and metamaterials, with its ability to confine light down to nanoscale, to dramatically increase coupling efficiency, in this case photonic density of states, could make these quantum processes more pronounced, stronger. And therefore I believe that not only future quantum photonics will be hybrid, not only in terms of materials used, but also in terms of ideas borrowed from other areas, such as plasmonics and metamaterials. And remember that ideally we would like to convert these single photons to telecom wavelengths. Like in this case I just showed, single photons were generated in the visible. We need to convert them to telecom eventually. And the way it could be done, like let's say if I have a single photon at 700 nanometers, like in the case of nitrogen vacancy, if I have here this single photon, and if I apply pump at 1.5 micron, in this case many photons, because of the down conversion, you would generate also single photon, but at 1.3 micron. So that's the way to convert single photon from the visible to single photon in telecom wavelength. So that's something to consider. So as I said, you either directly generate single photons at telecom, which might be a challenge. It's near infrared and particularly at room temperature, or you do it in the visible and then convert it to telecom. So people pursue different directions. In my opinion, although it might change, it depends on materials we have at hand. That way might be more promising. And I mentioned that with nitrogen vacancy, it's cool. You could couple it to spin degree of freedom, to quantum memory, which is important. You could control it, and it's long-living. However, the width is broad, meaning that to make single photons with the same characteristic, it's rather hard. You would certainly prefer to work with something which has much more narrow bandwidth. And if it's really narrow, and if you emit photons within the time which is shorter than decoherence time, then you would generate indistinguishable photons. But to make this happen, the width should be narrow, because if the width is narrow, the coherence time is long. Then we should be able, by using strong Purcell enhancement, strong resonator, or let's say like hyperbolic metamaterial, you should be able to emit many photons within the coherence time. That would make them indistinguishable. And the promising way to go is actually to use silicon-like vacancy, or perhaps germanium-like vacancy. Because in this case, you have really narrow line widths, 1 nanometer. So what you could do if you employ this type of vacancy with very narrow line, and if you would have very strong enhancement in efficiency of generating photons, so that the photons again would be generated within the time which is shorter the inverse of the width, meaning that which is shorter than the decoherence time, then you would get indistinguishable photons at room temperature. For that, you need to have very efficient enhancement in terms of this rate of generation. And that's exactly what our group and some other group working to accomplish. So in this particular case, you need to have dramatic, so-called very high Purcell factor, the level of several thousands, to increase the probability of emission of single photon, so that you would emit several photons within this decoherence time. And it's possible, but for that you would need to have a really nice plasmonic structure, which can provide a very strong Purcell factor. And that's exactly what we are trying to do, and I'm sure other groups in parallel. So again, I guess to sum up what I would like to deliver today is actually not only we should look at different material platforms, but also see how the ideas in Plasmonics and Metamaterials could increase the efficiency of important processes related to quantum photonics. And one of these is generation of single photon. Another one is related to so-called spin register, which we will consider next Monday.